Hello, everybody. I'm very happy and pleased to be here today with you. Thank you very much for attending. We have a lot to cover today, and we're excited about this presentation. I also have here with me Mauro, which will be supporting me with any questions that you might have regarding VI-CarRealTime and any of the solutions available by VI Grade. So I want you to jump straight into it because we have a lot to cover in today's webinar. So before that, just a few quick words about us. So MOVEdot, we are a company with a single and very clear mission, which is to 10x the vehicle development efficiency. So we see a future where things are done a lot faster, a lot cheaper, so that we can focus on creating new technology. So we have areas that are taking care of designing, testing, developing processing data for vehicles, being them road vehicles or race cars. Besides that, another focus of ours is creating methodologies to be implemented at our customers. So we don't want to only execute a service. We want to create this methodology together with our partner or customer and then deploy it in-house so that they can take over and proceed with their work. So in this case, we were developing a methodology for KNC testing at one of our customers. Besides that, developing also testing methodologies, data processing methodologies, seminars at our customers to teach all of the engineers the methodologies that we came up together. Besides that, we also do motorsports. So there is a lot that we bring from motorsports in terms of efficiency. And then ultimately, we're here to create new technology, to use the latest technology and create very efficient methodology. So if you're curious to know a little bit more about our work, what we do, you can take a look at our social media accounts in this link or QR code. And I also post a lot on my personal profile on LinkedIn. So without further ado, I wanted to say that for a lot of our projects and methodologies that we develop in our customers, we count on VI Grade's technologies. And this is why I'm so excited to be invited to show a little bit of how we use their solutions. So whenever I'm showing something and presenting something, I like to bring a case study, because with that, we have a real example showcasing all of the different technologies and methodologies that we want to discuss. So for today, we have 45 minutes, more or less, before the Q&A. So we're going to try to tackle a simple yet very interesting case study. So in this case, we're going to assume that we are an OEM and we have a finished road legal car and we want to convert it, or a road version, and we want to convert it from this road version to a track focused version. Basically, for marketing reasons, we want to beat the lap record of the Barcelona circuit in this example. And we're going to be discussing how we can use modern technologies to achieve that in a very efficient way. So in this webinar, we're going to be covering more the methodology and mentality behind this development. If you want more specific, if you're looking for more specific details on how to use and operate VI-CarRealTime, we're also developing a video series together with VI Grade with that purpose. So if you go on YouTube, you can very easily find that if you type VI Grade tutorials, or once again, you can find that information in our QR code. I think that you really enjoy to learn how to operate and manipulate and use the software. All right, so a few quick words about the traditional development that we do not want to use, and then followed by a comparison with the digital twin-based development. So in the traditional development, we would have the baseline vehicle that is our reference. We would define new targets for this vehicle, and then we would start prototyping new components to try and achieve our intended goals. The problem is we're going to have to prototype these parts, or actually do the tooling to manufacture these parts, then fabricate these components, go to the track, and then test it. The problem is when we get to the track, we'll not achieve what we wanted. Maybe we needed more mass reduction. Maybe we needed more power. Maybe we needed a different damping setting, aerodynamics package, and so on. So proving ground testing, even though it is important at the end of the process, it is very time consuming and very expensive. Not only that, since we have a limited number of iterations that we can do when we're doing track testing and component prototyping, we risk getting only to a local minimum of our solution. So we risk not achieving all of the goals that platform, that specific platform was capable of achieving. So it is limiting us. And this is a very interesting plot that you might be familiar with. If you're not, I recommend that you take a look. There is a very interesting paper regarding this from Mandar Hazar, and a paper called An Integrated Systems Engineering Methodology for Design of Vehicle Handling Dynamics, and in which we're going to analyze the different phases of the project, so concept definition, design, prototype, and then testing. And we're going to see that if our approach is purely empirical and development on the track, project maturity takes a long time to come up. Why? Because when you are designing something, if you pass quickly through that and if you don't do any proper work in the virtual environment using digital twins, you only know if you're getting to the final specification of your vehicle when you're really testing it. So it takes a long time until you get to the track testing and development to increase your project maturity. On the other hand, cost commitment is very high because from the beginning, you're already testing things on track, having to do a bunch of tooling, having to manufacture many different prototypes, and the cost commitment is very high. And actually, one of the biggest downsides is that the project risk is still very high while you already have a lot of cost commitment. So you already invest a lot of money into the project, but the project risk didn't decrease. So you still have the risk, you are still at the risk of the project failing, or you not achieving your metrics, or the customer not being satisfied, or you having to recall your vehicles that are on the road. On the other hand, what we're here to discuss and give you a couple of examples is the digital twin-based approach for development, where we will have our baseline vehicles, we will define new targets, but instead of prototyping things and iterating things, we're going to use our digital twin that needs to be properly created. We're going to run a bunch of different optimizations and experimentations, as I'll give you a few examples. And then we're going to be running this virtual development before we can then go to the track to do the final validation of the vehicle, fine-tuning, verifying our digital twin, and then deploying the final version. In this case, not only we gain project maturity earlier on, but we also are a lot more likely to get to a global minimum. So in this case, we are not just trying to adjust a few of the issues. We're really analyzing our entire design space to make sure that we found the optimal result for that platform. So, and this is this section of digital twin iteration and experimentation is what we're going to be tackling here. So in that scenario, not only, as you can see, the development period or time is a lot shorter, we also have a lot lower cost commitment until later in the project when we start prototyping, because we know that simulation is a lot cheaper than real prototyping. Project maturity comes up a lot sooner, which is something that is really desirable. And at the same time, the project risk is coming down a lot sooner. So as we're doing a proper work with digital twins, we get closer to the final project. We know that we're meeting most of our criteria. And then on top of that, if we also use driver-in-the-loop simulators, hardware-in-the-loop simulators, once again, the project risk is coming down a lot sooner. So we have a lot less money invested, but we already have a lot less risk as well, which is something very good for us as an OEM. All right, so what will be the roadmap of our development together? So we are working with a baseline or reference vehicle, and we're going to define new targets or new vehicle attributes, meaning the final behavior of the vehicle. Something that we have to keep in mind is that even though here we are speaking about creating a track-focused version out of a sports car, the methodology and all of our discussion is also useful and valid for so many other examples, because very often we don't start from scratch, we start from a reference. Ideally an internal reference, or many times benchmarks that we perform, but we have that reference. And then we are going to define new vehicle targets for our next iteration of the vehicle. And we're going to discuss about defining these vehicle attribute targets. So once we have that, we're going to start with our offline virtual development, meaning we're going to be running simulations on our computer, and we're going to be using VI-CarRealTime for that. After that, the next step would be for us to incorporate the feedback of a human being, meaning driver in the loop simulator, and also the effect of the real hardware, because we're not always capable of modeling all of the details of the hardware. So we also utilize hardware in the loop simulators, or the integrating simulators with hardware. Before then, we go to track validation and fine-tuning of the vehicle. So here, our case study, we're tackling the offline virtual development with a focus on VI-CarRealTime and showing you how the software can speed up your development. All right, so what is VI-CarRealTime? For those who are not familiar with the software, I don't like to call it a vehicle dynamics simulation software and so on. I like to call it a vehicle model environment. Why environment? Because if you look on the right side of the image, where we can do vehicle dynamics, so we can simulate all of the platform, the mechanical platform of that vehicle, which is obviously very important. But not only that, we can integrate control systems. And we know that nowadays, cars are as defined by the control systems and software as they are by the mechanical components. But even though it integrates all of these different areas, it is straightforward to model a vehicle because we use a curve-based parameterization. So many times we don't have to have all of the details of the vehicle if we're able to measure the overall behavior of that car. For example, if we measure the suspension curves, we can directly input those suspension curves inside of the model, and we have already our suspension model. So it's very powerful to be able to work like that for fast digital prototyping. Well, now when we look at on the left side, this is also very important and explains why I like to call it a vehicle model environment. It is because it can very easily connect with driver in the loop, with hardware in the loop, with traffic simulation. If we use VI World Sim, it provides us a very realistic scenario with other cars, other players in our environment. And with all of that environment, we start also looking at control systems, ADAS, driver feedback, interaction with other vehicles. So as we can see, it's a lot more than vehicle dynamics, even though we're going to be focused on vehicle dynamics in this particular webinar. All right, so now that we have the software defined, we're going to start defining the targets for our new vehicle. So where are these targets coming from? Well, one big source of information for us to define our targets is benchmarking. So we're going to be testing a bunch of vehicles in very specific and rigorous testing, because then we can collect what other people are doing, what compromises they are able to do, compare with our vehicles, and define future directions that we want to follow. And of course, we're going to also be looking at the DNA of our brand, because basically defining the target is defining the DNA that we want for our vehicle, defining the personality of the vehicle that we're creating. So we also look internally and then compare it to the outside. Besides that, we're going to be looking at the voice of the customer, as we call. So it doesn't only matter what we feel and what our test drivers feel. We're also going to be analyzing our customers, what they feel, what they want, and how we can connect what they say versus our vehicle attributes, objective vehicle attributes. We can use simulations to understand all of the range, all of the performance envelope of our vehicles and digital twins. And one of the most important parts is not only collecting the data, but having a centralized database where we can put all of this information together and we can find relationships with them. So this is extremely important. With that, we're going to have all of the information that we need to define what target we're trying to achieve with this vehicle. So one thing that I always suggest is start simple. So let's try to focus on this project. What are the main parameters that we're trying to achieve? What are the main focus of this vehicle? So we are going from a road legal to a track focused car. So to start with, I only selected 5 metrics. So these are at the bottom. We have lap time, because one of our criteria for marketing reasons is to beat a lap record. Then I also defined suspension frequency, which is a big difference between a road car and a track focused car. Road gradient, the amount of body movement, car response or agility, and then finally understeer gradient, which is the balance of the car. I'm not going to focus too much on the details of each of the metrics because once again, we're here for more the methodology and how to integrate a simulation environment into all of that. Now, even though we defined a very simple set of attributes that we want to achieve, of course, we can expand on that and we should expand on that. And then the next tip is the more mature and advanced your simulation software and solutions are, and the more mature your team and procedures are, the more metrics you will be able to tackle. So if you have a very rudimentary and not mature software solution and team, you should start with few metrics. Otherwise, once you have the maturity and the experience, you can start tackling more of these vehicle attributes so that you ensure that you always get to the fundamental ones, but in the correct way, in the way that you want them. So in this case, we are using VI-CarRealTime, and it's going to allow us to create hundreds of targets if we want. For this webinar, we selected a couple. We selected maybe a dozen metrics. These are in the areas of steady state handling, transient handling, ride and comfort, as well as track performance. So for this race car, even though we are trying to achieve a minimum lap time or a given lap time at a racetrack, it will be road legal, meaning that we still need to have the handling characteristics, the steering feel, the safety, the stability that a conventional road car, as a conventional sports car would have. So this is why it is important that we look at all of these metrics. However, when we are designing a real vehicle, not in a case study, we're also going to have a bunch of other attributes such as traction and braking performance, stability, energy management, particularly in hybrid and electric vehicles, torque vectoring, ADAS systems, and so on. So we're going to define a bunch of metrics, and VI-CarRealTime is helping us to define all of them. So when we are working with simulation, not only we can work with many different metrics and targets that would be very hard to do in real life for you to quantify all of that, to be consistent, and to have the time to do all of that testing. Not only that, it allows us to get more understanding. You're going to see that it is something that I will emphasize a lot in this presentation. It is not only the final result, but understanding what is going on. We don't want to press a button, optimize a system, and just have the final value, because number one, it will not be perfect, and number two, we're not going to understand why we have that. What we want instead is an understanding. We want to understand the connection and relationship between all of these different areas. I'll give you a few concrete examples in a few slides. All right, once we are done defining what we want to achieve, which is the target, the final output, we also need to define what parameters we can play with, meaning what parameters we want to change in the vehicle from the first version to achieve the targets that we are discussing. So this is going from a design, defining the design space that we want from all of the possible variables, which ones we want to play with. How do we deal with that? In our case, we have a specific budget for this vehicle. So basically, we need to understand what components of the vehicle are going to give us the most performance in the areas that we want. When I say performance, it's not only lap time, it could be achieving a given target or feeling for the end customer. So what are the components giving us the most performance, and how much that performance will cost? We know that in the end, everything will connect to money somehow, as it should. So with the VI-CarRealTime, we can start understanding these compromises, because it allows us very quickly to understand the influence of each of the components, and then we can also do an internal study to understand the cost of that change. So let me give you an example. Maybe we realize with CarRealTime that we would need, if we don't change aerodynamics, we just decrease the mass, we would have to decrease the mass of the car by 200 kilos to beat the lap record. Well, we know that to reduce 200 kilos out of a car, that would be very expensive. It would, the R&D to develop those new components and new solution would be expensive, and to manufacture the final component for the vehicle would be expensive, raising the price of the car or lowering the profit margin as well. So we start analyzing all of these different compromises: mass, suspension architecture, aerodynamics, powertrain, engine power, regeneration, ADAS systems, active suspension. So which solutions are going to give us the best compromise in whatever areas we're talking about? Performance, comfort, and so on. So we're gonna use the software to quickly analyze that. With that, we can narrow down from our design, very wide design space, to the most efficient components. All right, so we selected the components that we want to change. So in this particular project, we found out that we are gonna have to develop a tire together with a tire manufacturer, which is something that us at MOVEdot we do with our customers, and we interface the OEM with the tire manufacturer. We are going to change the vehicle mass, the power. We're going to develop new aerodynamics. So the body work will be completely different. We need to redo all of the CFD and aerodynamics work, and a few suspension components as well. So this is how we were able to minimize the cost for the performance we're going to get. All right. So we are almost ready to start running simulations. Before that, we just need to make sure that we have our proper validated model, or ideally a digital twin. So in that case, we know that to validate a system, usually or ideally, we should start validating each of the components if we can. For example, tires, dampers, powertrain, and so on, before moving on to validating an entire system, for example, the entire suspension. Once we validate the entire suspension, as an example, we could be using KNC, a KNC test, a KNC rig. Only then we go ahead and we validate the entire vehicle. This is ideal because when we validate the final vehicle, of course, we're going to have discrepancies between the model and reality. But if we validated and we tested each of the components, we can understand where this difference is coming from. So we can very quickly adjust our model to fix that. So it's a very good way to do that. Not only that, it is very important that we mention that the digital twin part should be taking place as a routine task. So it is not something that, okay, we want to start a new project, so let's build our first digital twin before we can do that. Because whenever you have to tackle a project and you need to implement a new process on top of that, we know that it will not be efficient. Basically, you are creating two projects instead of just one. So ideally, the way that we would work with digital twins is to basically integrate digital twinning in your regular workflows and regular processes, so that whenever you're developing a car, you have a digital twin running in parallel to that, always being updated until the last version. Why? Because if you have any problems with that car, you need a quick iteration, you need a new version of that car, you already have your digital twin ready to be used. Your development will be a lot more efficient like that. So we know that not everybody can instrument and test a bunch of different vehicles and take the time and the energy to create digital twins. So something that is very interesting is that VI-Grade, they did this together with IDIADA, where they provide digital twins ready to be used. So if you scan this QR code, or if you look on Google or use this link, you can take a look at what digital twins fully validated they have available within VI-CarRealTime. So it is even easier when you already have a car that is validated, that you can use as benchmark or any other analysis that you want to do. So this, once again, increases efficiency. All right, so let's say that we have our digital twin. Now we have to define what maneuvers we're going to be running. It is extremely important that whatever maneuvers we are running in the digital environment, we are replicating the maneuvers that we do in the real world. Why is that so important? Basically because we want all of the results from these two sources to go through the same pipeline of data processing. So this is, once again, something that we very much focused at MOVEdot, helping our customers come up with a streamlined and very efficient workflow of data processing. So in this case, we want both our virtual test and real test to output a similar data, to go through the exact same processing scripts, get the exact same metrics and sanity checks to validate the maneuvers. And then this helps us to get to actionable conclusions in a lot more, in a way that is a lot more straightforward. Not only that, you can already see how this helps us connect or to get to that vision of having a vehicle development together with a digital twin development. Because whatever tasks we're doing with the real vehicle, we can quickly compare that with our digital version of it. So that's extremely important. I'm gonna highlight a few ways in which we can do that. In any case, we are now going to start tackling the simulations. So the first area that we wanted to discuss, as I mentioned, is handling, and we're going to be doing steady state first. So let's start simple first. So we're going to be running a typical maneuver, usually used from the ISO norm, which is a constant radius maneuver. So in this case, because of space constraints on the real life, we're going to be replicating the same maneuver in the simulation using the available space, in which we have a constant radius and we're slowly increasing the speed. Well, not that slowly, otherwise in real life, we're going to be overheating our tires. So we replicate that in the digital world, and then we will be looking at how much the steering is increasing, or our side slip angle, or our slip angles, roll angle, so we can extract a lot of metrics. The interesting part of doing this with VI-CarRealTime is that I don't have to set up that simulation. It is already parameterized for me. I just have to set a couple different numbers of what are the speeds, the radius, and so on, and then I'm ready to go. So it's very quick from the get-go to get these simulations running. So the next step for us is to look at the results. So in VI-CarRealTime, we already have an analysis environment, VI Animator, where we can see the plots and we can see the real vehicle, which helps a lot for troubleshooting and understanding the simulation results. But not only that, as you probably noticed, I like automations. I like automated processes. So the interesting thing is that VI-CarRealTime already provides me with an auto-generated report. So as soon as I'm done with the simulation, I have this report generated automatically. And the most interesting part is that the script for this report is available. So I can just modify it to do whatever I want. So include new metrics, include new plots, and provide the plots that I want to analyze. So once again, emphasizing the need for automation. And with that, we were able to conduct our steady state vehicle dynamics analysis, going from the red curve all the way up to the targets that we define. So as you can notice, the wider you go, the more similar to a race car or to a track-focused car we are in the way that we organize this radar plot. So obviously, it's not as straightforward as you run one simulation and you're already achieving all of your targets. There are multiple sub-experiments that we're going to be doing, trying to understand the influence of each of the parameters and understanding what parameters we want to change. Always focused on gaining understanding on our system. And I'll give you some examples in the next slides. Okay, so we were speaking about automation. So before we move on to the next maneuver, I would like to show you some other ways in which we can integrate Python within VI-CarRealTime. So whenever we're running simulations, let's say that there is an extra output that is not provided by the software. Let's say that I do vehicle dynamics and I look at cornering compliance of each of the axle, which is, by the way, a very useful metric, but I define it in a particular way, which is different from the way that VI-CarRealTime defines. I can create a Python script for that, integrate it within the software, and then it's going to provide me with the results inside the software. So I don't have to necessarily do post-processing totally outside the software. I can have that integrated. Not only that, but I also, when I'm doing experimentations using investigation mode, which we'll talk about, I'm also able to create custom metrics with whatever processing methodologies I want using Python. Once again, this is something that we develop heavily for VI-CarRealTime. So if you have any needs on that front to developing these automated methodologies, you can definitely contact us and count on us. All right, so we're going to be using that, and we will speak about the next maneuver. So once again, a predefined maneuver within CarRealTime, which is giving us the transient characteristics of the car. So this is a step steer. We are driving in a straight line, constant speed, and then we have a very aggressive steering input, as you can see. Since it's already parameterized, I just have to populate with a couple of parameters that I want, and it will perform the maneuver for me. Once again, I will then look at the results within the software, verify that everything was okay, have my custom plots and custom reports automatically generated, and with that, I can calculate, once again, automatically all of my metrics. What you can notice here is that this time, since now we're starting to look at steady state transient, I was not able to achieve all of the metrics on the first shot. And this is normal. We're not here to be perfect. We're here to do things efficiently and to gain understanding. So I don't want to spend months just running iterations to get this first maneuver right. The way I like to do it is to do one complete cycle of all of the different maneuvers that I'll have to optimize to gain understanding about my system, to get a general understanding of in what direction each vehicle attribute is trying to pull each of my components, in what direction it is trying to say that the spring should go, that the bushings should go, that the dampers or the active systems or ADAS should go. So I'm going to do one full cycle, and then I come back to fine tune and refine and understand the trade-offs. All right, so before we move on to the next maneuver, there's something very, very important that I want to talk about. When we speak about digital twins, usually we are speaking about just the vehicle, the mechanical platform, but we have to understand that there is a lot more than just the vehicle or than just the mechanical platform. We need to make sure that we have digital twins, not only of the mechanical aspects, but also control systems and software environments within the car. So we need to have a validated model for all of the different systems. And we can go even further. We could say that we also need digital twins of the outside environment, because otherwise how we are going to develop your systems using offline simulation or simulators if you don't have validated models of the outside world as well. So in that sense, sensors are particularly important because you need to create sensors within the digital world that will do a similar, that will have a similar performance or behavior than the real world. So digital matching real world. So in that sense, in order to have a similar maneuver in the virtual world and the real world, you need to have the sensors placed in the same positions. So in this example, the next maneuver will be ride maneuvers. We know that to develop ride, we're placing specific accelerometers in specific places of the vehicle. So here, in this example, we want to analyze comfort on the passengers or on the driver's seat. So we are installing an accelerometer at the seat rail, not only on the real car, but also in simulation. And VI-CarRealTime allows us to do that, to install the sensors, whatever we want, to replicate the vehicle and connect it to whatever bodies we consider relevant. So with all of those accelerometers installed also in the simulation, so that we can look at the channels and later on validate against our real car, we will perform maneuvers, ride maneuvers. So the first maneuver will be speed curbs. With speed curbs, we're going to be looking at maximum values of acceleration when we have the impacts on each of the axles. Well, luckily in this vehicle, we have only the front seats. We don't have a back seat to also analyze and decide the trade-offs, but it is something that we could easily do here. So here we look at maximum values of acceleration and maximum values of body motion, as well as the dissipation of this energy, such as pitch damping, for example. Once again, VI-CarRealTime will provide us with parameterized ways of defining that. So I have a constant speed maneuver, but I can change the road profile to whatever I want. And when I change the road profile, it is providing me with a very simple way of defining the radius of this speed bump. It is important to know that when we are doing ride analysis and VH analysis, we need higher accuracy tire models. So Passeica models will not be enough to have proper data for that type of analysis. But VI grade provides straight away a connection with CD tire, F tire, TAME tire, MF tire from Siemens, and also Mega Ride's model, which is the 3D ride. So it's very easy for me to plug whatever tire models I work with to do ride or NVH. So for ride, besides only looking at the impact, we also look at another maneuver, which is very, very simple to model or to have running inside VI-CarRealTime, which is random inputs. So random inputs, we are basically simulating a rough road with a lot of bumps. And in that case, I can input and define the road profile based on PSD parameters. As you guys know, PSDs are giving us the power dissipated or the power provided in each different frequency of the signal. So I can measure this PSD from the real car to get an idea of the track profile, and I can use similar parameters on the simulation. Once again, it is very important that we have the same environment for the simulation as we have for real testing. All right, so I have these two simulations running. Now I need to extract the metrics. So we know that the processing of these metrics are a little bit more complex than handling metrics. If you need help with any of them, we can definitely support you with developing these scripts. So the upper plot, we have the impact after an impact strip or a speed bump. And below that, we have an analysis of PSD to understand comfort levels of the vehicle. So the first one is impact. The second one is acceleration oscillation levels that define the comfort of that vehicle, how passengers feel. So we're going to use our Python scripts and automations once again to calculate all of the metrics. Here, we were able to achieve some of our metrics. We lost in other places, but once again, I don't want to overly worry about this now because I'm still in the process of gaining an understanding. So, but you can start seeing how many trade-offs we're going to have to make, even though we are only looking at 4 different attribute types. So the last analysis that we run before we can close the cycle and show the conclusion of the project and how to put everything together is the track performance, because in the end, not only we want the car to have a given feeling or to provide this feeling to the driver, we have a very clear target. We need to beat a lap record at the Barcelona circuit. So we'll be doing track testing and track evaluation also in the digital world with lap time simulation. So we will use this opportunity to install and to optimize our aerodynamics package. So as I said, we developed a new aerodynamics package, and we can now use this opportunity to optimize it. So for those of you familiar with race cars, we know that when we install an aerodynamics package providing a lot of downforce and performance focused, we will have what we call aero maps. What are aero maps? Aero maps are defining how much downforce, how much drag, and how much downforce distribution, or the balance of aerodynamics, versus the ride heights. So the height of the front axle and the height of the rear axle. So in a race car, when you change the heights of the cars, the axles, not only you change kinematics properties as you would in a passenger car, you change a lot the aerodynamics performance. So we're going to be using VI-CarRealTime to optimize that performance. It is very important that not only we're focused on creating new components, but whatever components we have, we make sure that we optimize that. So we're going to input the aerodynamics parameters within the software using these tables. Next, we need to model the track. So for that, there are different ways in which you could model a track or a circuit within VI-CarRealTime. Here, in this simple example, we use Google Earth to extract the path of the track using KML or KMZ files. And then we have VI Road, another module that allows us to create the race tracks. Besides creating the racetrack itself, we can also define the road roughness if we want, which is very interesting and very useful. So if we have a laser scan of a circuit, which is the ideal scenario, we can also use VI-CarRealTime. So as you can see, if I have not a lot of resources, I can do what I want, the analysis. And if I have a lot of resources, I can count on the same technology for that as well. And besides that, VI World Sim, which is the package that I mentioned, the solution that provides a realistic representation of the real world, is providing also many racetracks. Besides proving grounds, it also and scenarios and cities, it's also providing racetracks. So if you search for that on Google, you could find, and even the Barcelona circuit, as you can see in the pictures, is also available. All right, so we defined the vehicle by changing the aerodynamics package. We defined the racetrack. Now we need to define the experimentation that we're going to do. If you remember from the first maneuver, I said that I'm not just randomly playing with parameters or in one shot finding the results. I'm running multiple experiments. How do I run experiments with VI-CarRealTime? I use what we call investigation mode. So in investigation mode, we have all of the design space of the vehicle, basically all of the components that you have on the vehicle. Then we have the parameters that you can be working with that you want. So you're going to pre-select parameters that you want to change, and then you define evaluation metrics. So what CarRealTime will do is to select a given combination of all of these parameters, which you can define what strategy you're going to use for these combinations, and then it's going to run this thousands of simulations if you want to provide you with the results. So this is another case study, another investigation or project that I was doing using VI-CarRealTime, where we were running 3,000 simulations. So we wanted a very comprehensive understanding of the influence of each parameter. So here on the left side, we have the working parameters. So we have a parallel coordinate plot with all of the values of the inputs and then the values of the outputs. And then I could use a similar study to optimize aerodynamics. That's what we're going to do now. So if you watch the video, we were able to find a specific ride height combination of front axle and rear axle that provides the highest or the fastest lap. So as you can see on the straight line, we have one vehicle being faster, but as you start to corner, you can see that there is actually an optimized solution. So we're going to be using the animator and the analysis plots to understand where each solution is faster. And then we're going to be able to select the optimum compromise and optimal position for the vehicle ride heights, making sure that we maximize the performance that we have on the vehicle. Besides that, we could also optimize the wing angle. So once we gain an understanding of what's the aerodynamics balance that we want, the downforce is split between front and rear axles, we could also optimize the wing level for that given aero balance. So once again, doing an analysis using investigation mode showed us what was the fastest configuration. So let me give you a snapshot of everything that was done so far so that I can show you how everything connects. So stay with me. First, we started analyzing handling. We did steady state and we did transient. We did one iteration of that. Then we did ride. So we analyzed rough road and we analyzed impact strips. Then we did track performance. Then we did track performance here at the bottom. So we closed the loop once. But then what I want to do is after I gained a general understanding of my problem, of what components I'll have to define trade-offs, what even vehicle targets are not possible to achieve at the same time. Once I gain this initial understanding, I can come back to each of them and run specific investigations or experimentations. So let me give you an example. When we're analyzing ride, for that vehicle, is it better if we get better ride coming from springs and dampers, or actually I have to change bushing stiffness? Which one solution is going to give me the best ride performance, but without compromising handling and track performance? So this is the type of sub-investigation that I'll be running. And then I'll be running these iterations and sub-investigations to optimize each aspect of my system, gaining understanding of it, and on top of that, achieving a global minima in the virtual world that, if done properly, when I put the real car on track, will not be far away. After that, if we want to optimize this process even further, instead of doing all of this analysis manually, such as setting up the simulation, setting up the different aspects that I want to investigate, the different components, running the simulations, looking at the plots, processing the results. I can automate all of that with the API of VI-CarRealTime. So the way that we prefer to work is we define a script where we define a DOE, a design of experiment that we want to run, meaning we map all of the vehicle configurations we want to test. Next, we have all of our simulations predefined and pre-configured so that we can run the simulations automatically for all of the different vehicle configurations that we decided. After that, we have the results plugged directly into processing scripts. And after that, we have the plotting and the reporting automatically done as well. So with literally the click of one button, you can run all of these different steps, speeding up and increasing the efficiency of your development. So you can do all of that through code in case you prefer to use the API. Not only that, if you want to connect VI-CarRealTime with control systems within Simulink, for example, you can also do that. So it's very good to have this environment that you can carry to in whatever directions you need and fits best your workflows, which is very important for us when we are supporting our customers develop their own procedures. And then, as a conclusion to our design, on the video, we can see that we designed a car that is a lot faster than the other, has a lot better performance. Not only it is faster at the track as we're seeing, but it achieves all of the targets that we defined after a few iterations, and ultimately it beats the lap record as we defined. So now we know what components needed to be changed. We know what components were the most efficient to achieve that performance while still meeting all of the other criteria that we wanted, and we are then ready to go to the next step. We're not covering the next step here, but what would be the next ideal step? We would be integrating all of that into hardware in the loop and driver in the loop simulators. Why doing that? As I said, we cannot always characterize everything from the hardware, so we can also experiment and develop the hardware connected to a simulator, and ultimately we need the driver feedback as well. So if we're able to do the driver in the loop and hardware in the loop development, also using simulators, when we get to the final vehicle at the track, we should be very close to a final solution. So once again, minimizing test time, gaining project maturity a lot early on, decreasing the risk of the project earlier on, and then ultimately minimizing costs and developing vehicles faster. And as you know, our mission is to 10x vehicle development efficiency, so nothing more optimized than reducing the number of prototypes, as is the mission for VI grade. So guys, this is what I had to show for you today. Stick with us. We're going to have a Q&A session. I think we're going to have interesting questions. If you're interested in VI-CarRealTime and would like to request a trial license, you can access this QR code from VI Grade, and the same for validated vehicle models that I showed in the presentation. Besides that, to know more about what we do at MOVEdot and how we do it, you can also scan this QR code. We publish a lot of content in our LinkedIns, both MOVEdot and mine. And if you need any help with optimizing your internal processes, creating new methodologies, optimized and automated ways of doing data processing and integrating also VI grade solutions into that, if it is one of your struggles, you can definitely count on us. So I leave the connection for the company and also my personally or my work email. If you want to chat about anything, it's going to be a big pleasure. So that's it. Thank you everyone for your attention.